you can just multiply magnitudes and add the angles. Like you are multiplying 6 into 2, that is 12, and 70 plus 30, that is 100. So, and similarly, when you do division, you will do 6 divided by 2, that is 3, and then angle minus angle, that is 40. So that in that case, that is easy. And the reciprocal of c theta is actually 1 over c theta, that makes is minus theta. So if you have, you know, reciprocal or conjugate of complex number, that is just having negative sign with its imaginary partner, okay? Sounds good?
Yeah, it sounds good.
Okay. So now, so what conjugate means, that if you have something here in the first quadrant that is having, because you know there are 4 quadrants. In the first quadrant, there is plus plus, like your x-axis is plus, your y-axis is plus. In second quadrant, your x-axis is minus, your y-axis is plus. In third quadrant, your x-axis is minus, your y-axis is minus. In fourth quadrant, your x-axis is plus, your y-axis is minus. That's why, because it lies in the fourth quadrant where your x-axis is plus and your y-axis is minus, that's why it's shown in the fourth quadrant. That is the conjugate of the complex number. Okay?
Yeah.
Sounds good.
Okay. So, I mean, you can do this by just trying how you can do a by b and a into b. I'm not going in the, like this is the exercise problem to solve polar to rectangular and rectangular to polar, so that you will be here to, like you can practice and see that. Okay. So how it relates, how this complex number theory relates to our AC circuit analysis. Okay, so we transform sinusoids in complex numbers in polar form, and then solve the problem using complex arithmetic, then transform the result back to sinusoids. Okay, to solve the problem that involves sinusoid, we use phasor transform. What it means, we will see that too. Okay, so how, first of all, well, what we learned, that a complex number can be represented by a magnitude and angle, right? That's about it, that we know. Now, we have a sinusoidal signal that we will be using as our input. This sinusoidal signal that we will be using as our input has voltage as on its y-axis, and time axis is on the x-axis. Now, as it is a sinusoid, so they said that if your time axis is omega t, where your omega is rotation frequency, or 2 pi f, you say, then if you represent your x-axis here as omega t, and it's in terms of pi or 2 pi, then you can write it as this, okay? In this scenario, this is your maximum value, where this is Vm, okay? And if it is a sinusoid, either you can represent it as sine or you can represent it as cos. So how do you know this is a sine or a cos? Because if I say this is Vm sine omega t, and if I put omega t is equals to 0, in this waveform, it is 0. Like here you can see, here that at this point, if I'm putting omega t is equals to 0, which is the starting point, then your Vm sine omega t is 0, right? So what I'm saying is, this can be represented as Vm sine omega t. Okay, or this is actually, this is a sine signal, which is, do you know sine and cos trigonometric functions?
Yeah.
Right? And have you plotted them like sine theta or cos theta?
Yeah.
Yeah, sine starts at 0 and cosine starts at 1.
Yes, so that's exactly the same scenario. So this is omega t, which is our argument here, right? So we are saying it that when your omega t is 0, your Vm is also 0, which makes that this is your Vm sine omega t. When this is maximum here, so it may, let's say this is pi by 2. So then your Vm sine pi by 2 is Vm, which is giving you the maximum value. So this waveform pretty much represent as Vm sine omega t. That's what it is saying here. So that's what it says here, that it represent Vm sine alpha, where alpha is omega t. Okay, but they are trying to convert it in the form of rotational frequency, which is angular velocity of phasor, which is omega. So they are saying that if I convert this waveform into this form, then this is the magnitude, maximum magnitude Vm, which is this thing. You have the maximum value of Vm, and alpha is the angle. Like if you are saying that this waveform is Vm sine omega t, so as this waveform move like this here, this phasor will move in the circle, let's say. So if your alpha is 0, which is here, right, then this line should be at this point, like in the straight direction, because your alpha will be 0. Now, when your alpha is 90, then your phasor will be in this direction when your alpha is 90. When your alpha is 180, which is this thing, then this phasor will be in this direction when your alpha is 180. When it is 270, which is in this direction, then your phasor will be in this direction, which is your 270. And then when it's coming back after completing one cycle, which is 2 pi, then it will be back into its original position. Sounds good?
Yep.
Yeah.
We will learn it more, okay? So I'm just trying to describe how this rotation is linked to this waveform, okay? So that's how we describe the phasor with sinusoid, okay? We will learn this, okay? You don't have to worry about that. Okay, so in the phasors, you all actually know these formulas. Like you know that if you have cos omega t plus theta, you can write it as sine omega t plus theta plus 90. And if you have sine omega t plus theta, you can write it as cos omega t plus theta minus 90. And similarly, you can write it in this form. But you know, cos omega t plus theta is actually equal to cos omega t cos theta minus sine omega t sine theta. Similarly, your sine omega t plus theta is also equal to sine omega t cos theta plus cos omega t sine theta. So these are just the formulas that you need to refresh in your memory, because you may need to convert them interchangeably in each other. Okay. Now, what does this phase come from? We will learn that. You don't have to worry right now. Okay, but we still know that we are familiar with sine omega t, okay? And what is RMS? We all the time hear RMS. What is RMS? We will learn about that too. So Vm is the peak voltage of the sinusoidal waveform. And Vrms is calculated as Vm by under root 2. So this is 0.707 into Vm, which is the peak voltage. Now the voltage phasor of RMS, you can write whatever V of t you have, you can just write Vrms theta. Similarly, if you have this current, you can just write IRMS, Im over under root 2, and IRMS theta. So what is IRMS? That's what we need to learn. So actually IRMS, because you know that in the sine signal, it's varying up and down, it's oscillatory behavior. So average value of the sine signal is 0 because it will cancel out each other, okay? So RMS, we need to know that how much average power, much equivalent average power your sine signal is transferring to the load equivalent to DC voltage. So that RMS tells us. So RMS value of an alternating current is the steady state current, which when flowing through the given resistor for a given amount of time, excuse me, produces the same amount of heat as produced by the alternative current when flowing through the same resistor at the same time. Means that if you have this DC voltage here and you will connect it to the resistor, this DC voltage will produce approximately the same amount of current as this RMS voltage will produce. So RMS voltage is we need to know because it is equivalent to your DC voltage. Okay?
Okay.
Sounds good.
Okay. So we don't know, still we know about that. We said that we know that what is sine omega t, but we don't know about plus 30 and stuff like that. We will learn about that, okay? So what they have done here, they have said that if you are given just sine omega t, 100 sine omega t, you can just find RMS voltage like that because 100 is your magnitude and you don't have any angle, so you will just write 0t. But if you have 45 here, you can say that 45 is my angle, okay? So let's see what it means. So we are saying here that sine omega t plus theta, right? So sine omega t is our signal and plus theta is the phase. So plus theta represents the phase here, okay? So if your signal, what it means, just a minute, I'll tell you this. So this is your normal signal, sine omega t, which starts from 0, okay? And if you have a signal which does not start from 0, and it actually starts from something else, then you will say that it leads or lags by certain angle, okay? So let's see. This starts from 0, which means that in this scenario, your V and I are just sine omega t, okay? But here, this does not start from 0. Actually, current started way earlier than the voltage. So we need to know what is this offset. This offset is actually telling us that this is a phase of the signal or the angle by which current starts earlier. So let's say if this is your sine 100t, this is your sine 100t, then it starts 30 degrees before your sine 100t, then this will be your 100t minus 30. So 30 degree is actually this angle that will tell us that how much difference these two signals are. Similarly, In this case, your current start later. So in this case, your 100T plus 30. This will be 100T plus 30 because this starts after the signal. Okay?
Okay.
Okay. So okay. So I told you that here you are seeing that your signal is leading. This blue signal is leading, which means that if this is your VM and if IM is leading, so at the rest point, like here, you already have an angle of blue line, but do not have an angle of red line. So that's why we are saying IM leads VM. So we are all the time talking about with respect to the zero time. So here you can see that this is not started yet. This phasor did not start yet, but it already has an angle. That's why this is a leading phasor than VM. Okay?
Okay.
Okay. I will not do that yet. Okay. So this is the important thing which we need to know, okay? So VI and VL, okay? So these have different voltage and current relationships with the capacitor current relationship, inductor voltage relationship, and Ohm's law, okay? So we will learn, I think, in ENG 212 as well, but I am just summarizing it here for the lab purpose. So we know by Ohm's law in DC circuit as well, and in AC it's the same, that voltage across resistor is IR, where I is your current, R is your resistance. But the current across capacitor is not simple. It's not just you say that it's the V by C or something like that. It's actually C and derivative of your voltage across capacitor. Similarly, your VL, like the voltage across inductor, is L, and that is actually derivative of your current through inductor, okay? So these are the relationships that we need to know for the current, inductor, and the resistor, okay? I know it's too much information, but you will know about this, okay? Why we are doing this, okay? So this is impedance. Why we are concerned with impedance here. So impedance is something which is related to inductor, capacitor, and resistance, okay? So like resistance is also an impedance. Capacitance is also an impedance, but they are part of impedance, okay? So impedance is actually, if I'm talking about in terms of resistor, it is written as R plus JX, right? Where R is your resistor. So all the circuits where you have only resistors, your X is 0, okay? So like there's like the circuits in which we have only resistors, your Z is equals to R, okay?
Yeah.
So you just apply your Ohm's law, V by I, and that will be V by I theta if it has theta, but in case of R, its theta is 0. That's why you will just apply V by I, and that's it. So Ohm's law for AC circuit is not V is equals to IR, but for it's V is equals to IZ. So Z also has the effect of R and X, where R is your resistance and X is your reactance. from where this reactance comes from, if resistance is just the real part, okay? So that's what we need to learn. So that's, I already told you that R plus JX, where R is the real part, which is the part of the resistance, and X is the imaginary part. But what represents X? Which devices, what devices are there that can represent X? That we need to know, okay? So this is this AC voltage that you have connected with the resistor. So you can see that resistor current and voltages are same. I mean, you can just say, you can just find out the current by V, like E by R, and that will give you the current, okay? So it's also the sine wave, and it's a purely resistive circuit, and you can say that current and voltage are in phase. I'm talking about current voltage of resistor, okay?
Okay.
So here your Z is equals to R, okay? Now in this case, again, for resistor, you can see that your angle is 0. I mean, you don't have any reactance part. If you are talking about A plus JB, in this case, this is A plus JB. So in this case, your A is R and your B is X. And if you are saying your X is 0, which means your tan inverse B over A, if your B is 0, so the overall angle will be 0 because you don't have any X, right?
Yeah.
Because this is actually equals to tan inverse X by R. In this case, your theta is equal to tan inverse X by R, and your X is 0, so your theta is 0, and that's why your ZR is just equals to R, okay?
All right. Sounds good.
Okay, let's move. Now, this is what they are saying. They are saying that if you have two resistors that are connected like this, you have I of t 14.7 sine omega t plus 39, you have to calculate VR1, VT, VR1 plus VR2, ZT, and compute VT, the result of. Okay, so total current is, they have calculated IM by under root 2, which is the peak current divided by under root 2, and then that will be equal to your total current, and multiplying both of them together will give you what you should say by applying Ohm's law. In case of when you are applying Ohm's law, you just have the 0 here, so it's okay. And then similarly, when you are having why do you think here they wrote 39 degrees?
Because the current function, if we're looking at 0, would only have 39 degrees.
Yes, I think there they should write here as 14.7 39 degree divided by square root of 2, because this comes from here. Okay, so then there VR2 to just multiply both the current and voltages, current and impedances, and the total voltage they have calculated VR1 plus VR2, and then total impedance is having a 0 degrees because it's just the resistors. And similarly, voltage, total voltage is both current and voltages is multiplied by each other. So if this is 14.7 sine omega t, then you just don't have to write this 39 because this 39 is not there. You just will do 10.39. This 39 will not there. This 39 will not be there. So it's just then 0 angle. Okay, sounds good?
I have a quick question.
Yes.
Where did the square root 2 come from?
So this is RMS value.
Oh, okay. Gotcha.
Okay.
Yeah, and then one more question. They choose 14.7 milliamps as the max current, which I get where they get the 14.7 from, but how do you denote whether or not it's milliamps or amps, or is it just default milliamps?
Yeah, it's just normally default milliamps, but because amps will be too much current, but normally it should be mentioned.
Gotcha, thank you.
Okay. So, okay. Now there is the fun part. Now we have an inductor here. Okay. So inductor is not that simple as a resistor. Inductor is a different commodity and it's something that different. So first I will tell you what inductor's impedance is. So inductor impedance is J omega L. Okay. So if there is in the circuit this inductor, then this Z is equal to R plus JX. Now your R is 0, then you are having only JX. What just JX is, as you have seen, that this is actually J omega L. Okay. So there are two parts. If I say that impedance, then I have to add J part in it. I have to say that J omega L. But if I am saying reactance, then I will just say omega L. Okay. So omega L is the representation of the inductor, which says that omega L is the impedance, where omega is 2 pi F and F is the frequency. So here omega is 2 pi F. And F is the frequency. So, which means that reactance is dependent on the frequency, the input frequency. So it changes, it actually increases with the input frequency. So that's how you will represent your inductor. Now see here, they have actually explained how you will get J omega L. So for experiment, you don't need to know, but for theory, you need to know. So I'll just quickly go through it. So you VL, they are saying L DIL by dt. So if this is Im sine omega t, that derivative will give you cos omega t, which is actually equals to sine omega t plus 90. So if you will find ZL, that is impedance, your ZL will be VL by IL. So you will just replace this value VL divided by IL, and still you will have this 90 degrees phase difference. Now the question arises that how this 90 degree phase difference you will say is J, right? So normally J is, I said to you that you can write this as omega L cos 90. That will be its real part, and its imaginary part will be omega L sine 90. Right? That's what we have said before, right? So omega L cos 90 will be equals to? What is cos 90?
0.
Yes. So it will be equals to 0. And omega L sine 90 will be equal to?
Omega L.
Omega L. So if this is A and B, which is A plus JB, which makes this as J omega L, right? I will explain it again, just a minute. But I'm trying to say that we got this omega L 90 degree, okay? But how we do know that ZL is actually J omega L, okay? So what I'm saying is, because this is magnitude and phase, so I can convert it into the rectangular form, A plus JB by, or this form, this is Z is equals to R plus JX by multiplying cos and sine. That's what I was doing before, okay? So this will be omega L cos 90 plus J omega L sine 90. So I can just write it like this. Right? Is it right?
Wouldn't the cosine also be multiplied by J?
Yes, I just write it here, but it's also multiplying here. Yeah. That's what your question is?
No, but like where it says omega L cosine 90, should it also be multiplied by J?
Yeah, that's a good question. So this is your A and this is your JB.
Oh, okay. From the equation
Yeah.
before. Okay, thank you.
Here, where is that? Here we said that, this thing. Or maybe before that. Here, you can say that if you have 560, you can convert it into this form by multiplying A with the cos and B with sine, where B is your imaginary and A is your real number. Okay?
Yep.
So if I was having omega L, (90°), which is the same as this thing. Sounds good?
Yeah, thank you.
Will, are you here?
Yes, I am.
So sounds good?
Yes, sounds good. Thank you.
Okay. So okay, so we are good till here. So we know that if there is an inductor it's in our circuit, it should be having omega L as its XL, and its impedance is J omega L, which is its impedance. Okay, so let's see. In case of your inductor, one minute. In case of your inductor, you can see that here your voltage and current are not at the same level. They are not in phase. okay? So if your current is sine omega t, your voltage is 90 plus 90. So we learned that plus means that it is lagging. Lagging means that it will start later than its current, okay? So here, one minute, that's what we know. So if this is start earlier, it's V2 is leading V. And if it starts later, then it's lagging. Let me see. So here your current is leading and here your current is lagging, okay? Let's see. Okay, so here you can say that your voltage starts earlier, okay? So it means that the voltage is leading and your current is lagging, okay? And if you see, so it means that this, if this is I sine omega t, so this should be something that will give you me the positive value, okay? Okay, sorry. Vm sine omega t plus 90, they are saying, okay? Let's see that it's giving me the positive value or not, okay? So how can I check that it's giving me positive value here or not? By this equation.
Check the quadrant.
No, I can just plug values in here and check.
Plug in 0.
Yes, plug here 0, right? And that will be Vm sine 90. Vm sine 90 give me Vm, right? Here, right?
Yeah.
So this means that if there is a, sorry, I was wrong before, but if this is plus 90, this means yes, where your voltage is leading your current by 90 degrees. So you can just plug the values in to see that if I am saying that this is minus 90, let's say. So Vm sine minus 90 is minus Vm. So it will start like this, right? Something like that, right?
So is leading and lagging determined by what we would normally refer to as the x-axis or the y-axis?
It's determined by 0 point, like this 0 point, the phase at this point, okay? So if it is plus 90 or it's more than this one, then it's leading. And if it is here, then it's lagging.
Okay.
Okay. It's confusing for me too, but let's go with this. Okay. So VL is leading IL because IL is I sine omega t and VL is Vm sine omega t plus 90. Okay. So okay. Okay, so now I is lagging behind VL, right? Yes. So we are saying VL by I, VL 90 degrees, and then omega L, and you are getting impedance as 90, even with the Ohm's law as well. Okay. Okay, so here they have given you VL with the frequency and L, and they are asking to calculate as VL. So VL is 40 volts and 30 degrees. And just a minute. This should not be 90 here. This should be 30 degrees. That is VL. So that is 28.330 volts. Now, if you want to calculate ZL, that is JXL, you are already given as 2 millihenry. You will just replace it here and you will find out that this will be equal to 90 degree and then it will be equal to ZL 90 degree. Now, if you have to calculate VL by I, you will just do VL, this VL, and this ZL, and find out the current, okay? And that should be it. But I think this should be corrected. This should be 30 degrees. Okay, so I mean, we will come back later here, okay? You don't have to go into too much confusion here, but just remember that this is your J omega L and this is your omega L here, okay? Okay, now about capacitor. So the capacitor in the capacitor is, if your VC is Vm sine omega t, your IC will become omega t plus 90, which will make ZC actually equals to omega t plus 90 here, and it will make this as minus 90. Okay, minus 90 means that voltage will be, minus 90 means that voltage will be lagging, okay, because current will be leading. So if I draw it here without looking into it, so if this is my current here, so now my voltage should be this one, okay, because this voltage is now leading, okay. Sorry. Sorry. Plus 90 says the current is leading and voltage is lagging. Okay? Okay?
Yeah.
That's what we learn here. This is so, I all the time mix it. So this is that if you are getting 90 degrees here, this is leading. So it means that wherever I'm seeing plus 90, that is leading. Okay, so this one is leading. Current is leading, then voltage. Okay, sounds good. Okay, so now the only difference you are seeing with the capacitance here is that the capacitor is minus 90 degrees and your inductor was plus 90 degrees, which means that your capacitance is opposite to your inductance. Like your inductance increases with the frequency, but your capacitance decreases with the frequency. So that's what you are seeing here, that your capacitance is decreases with the frequency. And again, one thing you can see here, that if you're 1 over omega C minus 90, so you can say your 1 over omega C cos minus 90 and sine minus 90, which will give you minus J over omega C here. So it means that you will have here minus J over omega C, okay? Because cos minus 90 is 0, but sine minus 90 is minus 1. So if you are putting it as A plus JB, it should give you minus J over omega C. Sounds good?
Yeah.
Okay, okay. So this is your capacitor. In this case, also you are seeing that your current is leading voltage by 90 degrees, okay? So if I just put it in this way again, it should be my reactance and impedance, and that's about it. So they actually tell you how you can remember this. So it's LE, the Iceman. LE is voltage, inductance, and current. So they are saying that voltage is leading the current in inductor, and and current is leading the voltage in capacitance, okay?
Okay.
So that's how you remember it. Okay?
Yeah.
Okay. Now, okay, so they are saying at DC, like you said, that capacitor acts at open circuit, but inductor acts as short circuit. And for very high frequencies, you can see that your inductor is actually 2 pi FL, which is very much proportional to the frequency. So if you increase frequency too much, your impedance will increase too much, or your inductor will become open circuit. But it is the opposite case for capacitor, like it's 1 over 2 pi F C. So if you increase frequency too much, it will be acting as a short circuit for capacitor. Okay, so that's about it. Okay, so now coming to the experiment finally. Do you think that is informational for you?
Yeah, it was good.
You will understand now what actually we are doing in the experiment, okay? So we will be doing 5th experiment of AC. So it's experiment number 5, AC. So it's page number 300 and 301. Okay. So in this case, they are telling you to connect the resistor with your function generator. So I will tell you, show you on LT Spice how you can do that. So then they are asking you to maintain peak to peak voltage as 4 volts. What is the difference between peak voltage and peak to peak voltage? We will see that too. Okay. And okay, so, and then you have to find your RMS voltage, because you need to find your RMS current, and then your RMS voltage divided by RMS current will be your R, that is your resistor. So let's try to do this, okay? So this is the circuit, but I just want to remove this inductor here. And connect the okay. So what I did actually here is, you can see I went to advance, and instead of going to pulse, I went to sine, and I did 9 volts, and I adjusted frequency as 50 hertz, okay, which is the frequency in the start of table 5.1. And I did okay. The resistor is 1 kilo ohms. Okay. So what I did, 9 volts. 9 volts will not give me peak to peak voltage as 4 volts. So peak to peak voltage means that from the top peak to the bottom peak. So if you have the peak voltage as 2 volts, your peak to peak voltage will be 4 volts. Okay. So Here, if I set what you should say, amplitude as 2 volts, then it should give me peak to peak voltage as 4 volts. So if I do hit here, you can see this is my waveform, and let's see. So if okay, so one more thing is that it's 50 hertz is the frequency I set. So if you see in the time axis, it's 20 milliseconds. It's just covering its one cycle. And F is equals to 1 by T. So if you put as 1 by 50, it should give you 20 milliseconds, okay?
Yeah.
So it's completing its first cycle at 20 milliseconds. Sounds good?
Sounds good.
If I move this cursor, so if you click on it, you can move this cursor, okay? So if I move this cursor, it is giving me the maximum voltage here, which is 2 volts and almost, and that is its peak voltage. So they are saying to know its peak to peak voltage, which is 4 volts, which I am seeing on the resistor. So when you are dividing your RMS current and your voltage, you should get the resistance. Now you learn that your RMS voltage was peak voltage by square root of 2, which makes 2 by square root of 2. But here they are talking about peak to peak voltage, which is 4. So that's why they are doing 4 by 2 into 0.707 or divided by square root of 2. Make sense? Or I'm speaking too fast. Make sense?
The peak voltage is 4, gets divided by square root of 2, and then what?
No, what I'm saying is that your peak voltage is 2 volts here, right?
Yes.
Your peak voltage is 2 volts. Now, what is peak to peak? Peak to peak is that you are covering all the peaks in one cycle. So you are seeing 2, 2 minus 2, which makes it 4 volts. Okay, so you are seeing that overall its voltage, peak to peak voltage is 4 volts.
Yeah.
Okay, so, but that's why I'm saying that the formula they are using in 5.1 is a little bit different than our formula that we were using in RMS voltage. We were just using peak voltage, that is 2 volts. So if we are using our formula that is peak voltage, we are also good because it's 2 volts divided by square root of 2, right? Which is 2 volts multiplied by 0.707. But as they are using peak to peak voltage, which is the double voltage, that's why they are doing peak to peak divided by 2 into 0.707, right?
Gotcha.
So that's what we are saying here. So you have to fill the table 1, but you know that your resistance is not dependent on frequency. That's why it should not change. Sounds good? Let's try. Let's try having it as 100 hertz, okay? Let's see our waveform will change or not. So increasing the 100 hertz makes frequency increase, right? So it increases your, what you should say, the frequency, but it should not change your resistance. So that's what you need to know by checking your current too. So your current and voltages are same. So it means your resistance does not change. Okay?
Yeah.
Okay. Similarly, if I increase it further, it will also not change because resistance is just the real impedance and it does not have any frequency part in it. Sounds good?
Yep, sounds good.
Now
Wait.
I want to add an inductor.
How would we solve? How
What?
would we solve for the current for IRMS?
IRMS.
Because you
Oh.
said it doesn't change, right? The current.
Yes. I'll show you. 1 minute. So it's the same as your IM divided by √2. That's what we were doing before. Okay?
Oh, okay. Just similar to the.
Yes.
Voltage,
It's
okay.
just similar to your current. I'm just checking. That's what we did here.
Thank you.
If I show you quickly, if you see in your slides, I think it's on, I don't know which slide it is. It's on slide number 27. Okay? In which we calculate the current, and that is
Thank you.
actually peak current divided by √2. Okay? Sounds good? Okay.
Yes.
Let's do LT spice. Where is that? Okay. So now I am going to add a inductor. Okay, so inductor value is 10 millihenry and 100 ohms, okay? So it's 100 and 10 millihenry, and I should actually reduce this time. It's 0.2 seconds, so maybe I do 50 seconds. Let's try that. What is this UIC?
I think you clicked skip initial operating point solutions. I think that's the difference.
Okay.
The bottom checkbox.
Here,
No, yeah, it went away now.
let's see. Okay. So, but I want to make sure. Okay. Okay. 100 hertz I am trying. So I will be seeing 5.2. So they are asking us to do 1 kilohertz, which will make it 1 kilohertz. So 1 kilohertz means what is the one time cycle? 1 over 1 kilohertz is?
One millisecond.
1 millisecond, right? Yes, so 1 time cycle would be 1 millisecond, so I think I should do it as 10 milliseconds. Okay, let's try. Okay, so I have to see voltage across inductor. Okay, so the voltage across inductor is 1 volt peak to peak. It's not 2 volt peak to peak. So I need to select a voltage that will give me 4 volts peak to peak. Okay, so which means I have to increase input voltage. Okay, so that's your inductor. And let's see what else we have to see. Voltage across resistor. So this is your voltage across resistor. You can see the phase difference, right?
Yeah.
And you need to see current across your inductor. So the current across your inductor is, actually I should put the nodes as well. So current across your inductor is red one, okay? So you can see different magnitudes and different phases as well, but let me just first make it more clear by putting the labels. So this is VL. This is VL. And this is VR. Okay, let's see. Or I think this is not VR. Let's try see that. Because this is 2 volts. Okay. And this is almost 1 volts, right? So so voltage across resistor will be VL minus V1, okay? But I want to see first voltage across inductor and current across inductor. We want to see that they are 90-degree phase difference or not, okay? Let's see that first. So VL. So VL is 1 volts approximately and current. So you can see here, I think, if I just try to see that when your voltage across inductor is maximum, your current across inductor is minimum, right? You see what I'm saying? If I just click this and move this cursor 1. So this is 1.06 volts and somewhere here, right? And the similar position, if I put the second inductor, like this cursor here, you can see that it's very, very low, right? Point. So the point I'm telling is that where your voltage across inductor and current across inductors are 90-degree out of phase to each other, right? You see my point is that we were saying that current and voltage across inductors should be 90-degree phase difference across each other, right?
Yeah, and they are right because of what you just said.
Yeah, but the point I'm saying here is that what you need to do in the table 5.2, okay, first let's make it 4 volts peak to peak, okay? Like inductor voltage, let's try that. Means the inductor voltage should be 2 volts. Almost there, right? So with keeping this at this, you will fill the table for VRPP, like the peak-to-peak voltage. Then you will find out your IPP, which is the same for your VR and IL, and then you will fill this table, right?
Should we use 4 or 3 point whatever for the voltage?
4 volts, what is the question?
Like you put 4, but should we use like 3.9 to make it more exact to like 4 to from peak to peak?
Okay, I see what you're saying. But in inductor, it takes time to stabilize its voltage, okay? So you can ignore this one. You just see this one. That's your question?
Yeah, but it like passes the 2 volts. So should we use like maybe a slighter lower value to make it more exact? Or
No. Use the value you're seeing. Okay, it's okay. Yeah,
Okay.
yeah. Yeah. So you can fill that table and you will see that with the increase in frequency, your like the XL will be changing. Okay. Sounds good?
Wait, are we making these on the actual breadboard too?
No, because we don't have the generator.
Oh, so this lab is just on LT Spice.
Yeah.
Okay.
Yeah. AC circuit analysis is on LT Spice. Okay. Sounds good?
Yeah.
Okay. Now we will be moving to part 3, which is capacitors, and we will be filling 5.4 table. Okay. And I am putting it in. Sarah, are we good?
Yeah.
Okay.
Oh,
Okay.
also, are you going to upload the video of this lecture?
Okay, I will. Yeah.
Great, thank you.
Okay, so okay, so this should be 0.1 microfarad and 100 ohms, and I should start with 100 hertz. 100 hertz makes 1 time cycle equals to 0.01 second, right? Yes, so it mean make it 10 milliseconds. Okay, I'll increase this at 50. Let's see. Okay, so it should not be kilohertz. It should be 100 hertz. Okay, let's see. Okay, so this is 4 volts peak to peak. No, it's 8 volt peak to peak. You know what I'm saying?
Yeah.
It's 8 volt peak to peak. So I should change. And do you understand that when we have connected inductor with in the circuit, our voltage reduced, but when we connected capacitor in the circuit, our voltage increased, right? So it also deals with the impedance of both of them. Both of them are opposite to each other. So I will reduce it to 2 volts to make it 4 volt peak to peak. Okay. So it's now 4 volt peak to peak. And again, you will see the current. It's hard to see the current. And you can see that at maximum, when your, what you should say, voltage is maximum, you are seeing 0 current. So it means the 90-degree phase shift between your current and voltage of your inductor. And you can also verify with the inductor and, inductor, I'm saying capacitor. You can also verify with inductor and capacitor circuits that which one is leading and which one is lagging. Okay, so you just have to fill this table by changing the frequency, and you will find XC with your circuit and your calculations, and draw the graph. Sounds good? Sounds good?
Yeah.
I think so, yeah.
Okay. Just keep in mind that here they are talking about peak to peak voltage. So peak to peak voltage is 2 multiplied by your peak voltage. So if you have 2 volts peak, so peak to peak will be 4. So that's about it, I think. And so I am hoping that 3rd November I will be having a lab. So I think you will be doing procedure 1, 2, 3, and 4. And I added only 3, but we have to do 4 too. And I will be discussing exercise in the class next time. You don't have to do exercises, okay? Sounds good?
Yeah, sounds good.
Sounds good, thank you.
Will this lab be due next week, like normal, next Thursday?
I will give it more time, okay?
Okay, great, thank you.
Okay, so you just have to do LT Spice. There is no hardware involved in this simulations. And when is your last lab? What is the date of your last lab? So we will have last week of November as Thanksgiving break, right?
Yeah, that's the week of the 23rd to the 20 whatever. So I think this
7th.
class is the 24th.
So when is your final exams?
It's like
Early December
11th,
usually,
maybe?
right?
It's
Late
in the
November?
middle of December or in the first week of December?
Like first week, I think.
One
Yeah,
of mine's is the
first week.
15th.
They're from the 9th to the 5th to the 16th or something like that. All the exams.
So, but I just want to confirm that our first week is available for the lab or not. I have to do that, okay? But what I'm saying is that your last lab weightage is more than your other labs. So maybe in the next lab, I will tell you all that what you have to, it's last lab is kind of the project lab in which you guys have to not do the project somewhere else, but you will be given some circuits that you will build by yourself and show me, that will show me your understanding of the lab. So I am trying to plan that each person have a different lab to do. So in that case, you will just show me the circuit, just submit your lab report and simulation report. And that report will be having more weightage than your normal labs. Okay, I think I have mentioned in syllabus too. So sounds good?
Yeah.
I think that 80% of your percentage is all the lab reports, and I think 20% was your last lab. So I will be giving you, it could be AC, it could be DC, it could be any other thing. So it should be different for everyone, but it should not be too much of the big project thing. It's just the one lab thing that you have to do. Okay?
Okay.
So you will have Thanksgiving break to do it. But for that last lab, I will take your questions regarding understanding the project, but I will not entertain questions regarding your solutions. So understand your labs as much as possible. Now you have the time to ask questions about them. But if you will ask question about last lab, I will take the marks out. Okay?
Okay.
Sounds good. Thank you for today and have a good day. Thank you. Bye.
Thank you. I actually have one quick question.
Yep. But although I am here, but those who want to be here and ask question, I'm here till 4:40. Okay. Yeah. Go ahead.
For lab 7, I thought I remember you saying something about exercise number 3 that